Talk about this one, ED302. This is another one where you just get to compile with and without address space layout randomization, and then to perform an exploit in the debugger so you can see exactly how it works. So first we want to observe ASLR. So you must have a developer command prompt. You have to have Visual C++ build tools installed. And so you click the start button and you find this list of programs and get down to the V's. Expand this, and you must use the developer command prompt, I think. Let me go back here and see which one. Yeah, we want the developer command prompt for Visual Studio 2019. You can't just use a normal command prompt. You have to use this special one created under the V's. So Visual Studio 2019 developer command prompt for VS 2019. All right, and I'm going to increase the font size just to make sure everybody can see it on the video. And there we go. All right. And shrink this a bit so it fits on the screen. All right. And now, all right, so in here, I make a directory and go there and I make this esp.cpp. And here's the code. So what this does is it's a C++ program that just has a main function, and in the main function there's inline assembly code. This is a feature of C that you don't use that often, but it is an option. You can add raw assembly commands in C. So in this function I move the ESP into the variable called data, which I defined as an integer variable, and then I can now just print out data. So I can just, all this program does is print a location of this object called data, which is on the stack. So it gives me an address on the stack of the main function. And then it says press enter to continue so the program doesn't stop. So I compiled that two different ways. First you compile it with no switches or EHSC, which are some harmless switches that don't affect the security features. And then you copy it to ESP2 and compile it without address space layout randomization, which is a two-step process. You compile it with the /C switch, which compiles it only to object code, and then you link it with the /dynamic base no, which will stop it from being dynamically relocated in memory. So that makes esp2.exe. And I've already done that here. So if I go here to the 127 folder and then do a dir of star.exe, I've got ESP and ESP2, and once again you can see that the ESP with address space layout randomization is 218,000, and without address space layout randomization it's only 210,000 because the relocation code consumes some space. So again, the more vulnerable version without the protection is smaller. And so if I run those, say esp.exe, it tells me the stack is FBF8F8B8, and if I just press enter and then run it again, I get a different value. FB, this time it's 1C, run it again, this time it's 8FF. So as you can see, the stack is randomly relocating to a different memory location every time I run the program. But if I run the ESP2 program, compiled without that protection, then I get 19FF24, and when I run it again, I get exactly the same value. So here you go. That's a program without randomization. All right. And now, that's all we've done down here. Compile it without. Okay. Now you have to have immunity and Mona, which you should already have installed if you've been doing these projects in the expected order. But if not, then there's steps here to install it. Immunity and Mona. And now, once you've got them, you can load your program, run pwd3 in immunity, and a new program? I think it is. You did ESP. So we created pwd3 somewhere up here, and oh, I see. Here's the pw3 program. So this is a program with a possible buffer overflow up here. All right, and again, you compile that without address space layout randomization here. And so you have pwd3. So this one prints out the stack pointer, and it asks you for password. So let's run that to see how it works. So here, if I do a dir, it's not listening to me. Okay, dir. All right, here's pw3 compiled down to pw3.exe. Let's run that. exe, all right. So it prints the stack pointer so we can see it, and then it asks me for a password. I'll just put in A, and it tells me fail. And if I run it again, the stack pointer is the same, an A. So this is a program that takes a password and has address space layout randomization turned off because this program is not relocatable. So that's a program we can try exploiting. So let's put that in the immunity debugger. And so that's here. I run immunity. Maximize the CPU window to get the usual view. Now I can do file open and go to C127 and then PW3 or PWD3. So there's the program. All right. Now let me go back to my instructions. We've got PWD3 open in the debugger. All right. Now I run it, and then I'm going to put in this password, and I found, as far as I can tell, you cannot copy and paste from a browser into the command line window successfully on Windows, so it's A through H 4 times each. So we're going to run it and put that in, and then watch it crash. So let me try that. So here we are in the debugger. So I run the program with the run button, and now it says paused here. Oh, there's breakpoints I put in before. Let me take out the breakpoints. We'll be putting them in later in the project. There's one, and there's the other. All right, now I'll do debug restart to get the program back to its original condition. Yes. Now run. And now in the corner it tells me the program is running. And so there's a window on the taskbar here which shows enter password. And I wonder if I can change the size of this. I might be able to. Yep, I think I can. Yeah, now you can see it. So now I can enter a password, and so I'm going to put in oops, I'm going to use caps. Okay. All right. Each letter 4 times, ending in H. And then I press enter. And down here you can see the program crashed with an access violation when executing 48, 48, 48, 48. And so I've got a standard buffer overflow, and it entered the instruction pointer. There's this. By the way, whenever you see something in the status bar, it sometimes vanishes as you click around. So if you ever want to know what should have appeared in the status bar, you can go view log to see it. And so now it tells you the program ran and it is access violation when executing 48, 48, 48, 48, which is as the 8th letter, so A, B, C, D, E, F, G, H. That's the H's. So the 4 H's ended up in the debugger. So I want to go back to the CPU window to get back to normal. All right, so now we know we control the instruction pointer with the H's, and we can find it. The stack is showing at the point of the crash, so we're going to follow it in a disassembler. So if you look at the stack here, the second value here is a return pointer. This is the, now when you run a program, it creates a stack frame, then it calls a subroutine and creates another stack frame on top of it, and it crashed. So this is the code that was running before the crash here. So if I right click that and follow in disassembler, I'll find the code that was running before the crash. And what I want to do is scroll, so this gets me back to the area of code that was involved in the crash, and what I want to do is just make this window wide so I can see the easy, helpful stuff, and then scroll to the top. Here we are at 409,000. Windows programs all like to run at 401,000. So if you just scroll to the top, you'll see here. Now I'm going to make the font a little bit smaller so we can see more of this window. So that's appearance, font all, and I think, appearance, font all, and I think system fixed is a little smaller. Okay, so here's the helpful stuff. This is the stuff that's almost C code, you can see here. And if I scroll down here, I'll see helpful things like here is some function being called with arguments, And when it calls a function with strings, I'll be able to read the strings and tell what's going on. So here's the ESP printing out the stack pointer, and here's where it asks me to enter the password. So now I'm in the area of code that I want to put in a breakpoint. So what's going on here? This is the enter password line, and let me just make the font bigger to hopefully make this more easy to see in the video. Appearance, font all. Let's go to this one. Oh, that's not, all right, anyway, I'll settle for what I've got here. I think it's readable enough. So enter password is here. So what's going on? This is pushing the parameters on the stack. This call is printing out that message, enter password. Now the next thing it does is read data from the user. So it prepares something here. This is something like a format string or something. And then it does a call here. So that call is the call that reads the password from the user. So I want to put a breakpoint on this instruction, so I'll see the condition of the stack before it takes the data in. So I press F2 to put a breakpoint there. After it returns from this call, it has read in the data from the user, which is what's going to cause the overflow. So I put another breakpoint on the next instruction. So on the call and on the instruction after it. Now I can watch the condition of the stack and see the overflow in progress. So I'll view, debug, restart. Yes. And let me just make one more attempt to get this to a bigger font. Font all. There it is. That's the big one I was using. I think that'll be nice now. All right. And now let me go back to my instructions. So we put in those two breakpoints. And now we're going to do an overflow, and we're going to run the win function, just like we did in several of the projects. We have to find the uwin function, so that'll be the first thing to do. Let me go back to the thing here, and if I scroll, so I go back up to where I was, up here, and once again, I'm going to have to go to the other font size to make it so we can see the helpful stuff on the far right of this window. So that was appearance, fonts all. I think it was OEM fixed font was pretty good. Okay, so now we scroll down here a few pages, and we find the ESP message and then the password message, and someplace down here we'll find the win message. There's fail, and there's you win. All right, so this address right here is the address that pushes the uwin function on the stack, and then it pushes some other parameter and does a call, which must be the print. So if I jump to this address, 401270, that will print the uwin message. So what I'm going to do is insert that address on the stack, 401270. All right, so let me go back to the big font here and carry on with the project, which is this one. All right, so we found the message, which is 401270, and that's what it was in my instructions too. Sometimes you find that your machine is different because of Windows versions or something, but in this case, my Windows version is matching the one I used to write the project. So we want to run the program, hit the breakpoint and stop, and we want to look at ESP and EBP and examine the stack frame. So let me do that. This is just what we did in Linux. So it's debug, restart. Yes, then run. It runs and hits a breakpoint, and a breakpoint message showed up briefly down there, and then it vanished, like I said. So if you can't see the message in the bottom left, you hit view log, and you'll see here, so it hit the breakpoint. All right, view CPU takes me back to normal. All right, and so now the window has opened here, and it's asking me for a password, but it's not yet listening for me to enter the password. Now, if we look at the stack, you can look at ESP and EBP, just like we did in all those Linux projects. ESP is FF00 and EBP is FF20, and these do change every time you run it, so it won't match exactly my instructions. So this is FF00, and you can highlight it just like we did in GDB and Linux. So there is the stack frame for this program. These are the temporary variables used by this program, and this is the return pointer, 401258. That's what's going to return back to the program when it's done running this subroutine that fetches the the password. So we found the return pointer right here at FF24. Now, if I run the program again, now it's running. Now it's asking for a password. So I put in that password again, AAAA D E F G H, and enter. That reads the password and then hits the next breakpoint. And now I can see right here, A, B, C, D, E, F, G, H went onto the stack, and the EBP is FF20. And if I highlight the stack frame, it goes down to here, and you can see I filled the whole stack frame and I hit the return pointer here with HHHH. So that's going to cause it to crash if I continue trying to go to this invalid HHHH value. So what I can do is I can manually change that value. You can insert it by right-clicking and editing this value. And I want to put in this 701240, which is the address of the win function, backwards. So I right-click this and edit. And down here, I put in the desired address, which is again 701240. So it's 701240. Okay. Now I click OK, and now you see this has changed to a pointer, and that's a pointer that points back into the PWD function. So now if I continue, that should perform the overflow attack, and if I look at the window, it prints you win. So I've just done the same thing we did in the Linux project in the Windows debugger, and hopefully you can see how it looks a little different in this graphical debugger, but amounts to the same thing as what we've done before. All right, and there's a flag you can find, and in early version of this project, I had people looking in the corner for the flag, but this message keeps vanishing, so it's better to hit View Log, and you'll find the flag at the end of the log. And then you can even write an exploit in Python to do this for you, but I made that not part of getting a flag because that's kind of annoying, and it depends on which version of Python you have and so on. But that's what I wanted to show you. It's just a graphical Windows version of a simple overflow, so you can see exactly how it works. So that's it. Let me stop this recording.